All right, so welcome to another riveting chemistry video. This one will be on states of matter. I'm guessing that at this point in your lives, most of you know the states of matter, which would be solid, liquid, gas, and plasma. So we're going to talk a little bit about each of these. So the basics of each phase. So solids, it's a fixed shape and volume where atoms are locked in place by bonds and intermolecular forces. It is the lowest energy of the four. Liquids have a fixed volume, will conform to the shape of its container. Atoms can freely move past each other, but don't have enough energy to separate. Gases, they have a variable shape and volume. Atoms have enough energy to overcome intermolecular forces and separate from each other than to move freely in all directions. And plasma, a high energy substance composed of ionized atoms and free electrons. So that is the four phases, and hopefully you're familiar with all of those. Basically, that solids, right? The atoms can't move around. Liquids, they can, but they can't kind of escape each other. And gases, they have enough energy and they are all over the place. Now, the transitions between each of the states of matter, I know some of these terms will be familiar to you. And so going from solid to a liquid, that's melting. Going from a liquid to a gas, vaporization. Gas to plasma, ionization. And then going the other way, plasma to gas, is recombination or deionization. Gas to liquid, condensation. Liquid to solid, freezing. And then there's also the ones that are directly solid to gas, which is sublimation. They're subliming. And gas to solid, which would be deposition. They are depositing. This is what is called an energy or phase change diagram. And basically it shows that as heat is being added or the energy is increasing, what is happening to the temperature. And so you can see that in the part way down here, you have a solid. The solid is melting. You then have a liquid. The liquid is being heated up. The liquid is then being boiled, right, and turns into a gas. Now, one of the things to notice on here, and I know a lot of people kind of struggle with this one, but that when you are melting a solid, right, that energy that's going in is not increasing the temperature. It is just going to break the interactions that are holding the solid together, and so your temperature won't increase until that solid is melted, right? Same with going from liquid to gas. The temperature does not increase while you are boiling that liquid away, and will only increase again once you have a gas that you're adding more energy to. All right, and so that is what's going on with the phase change diagram. And we have an equation that goes along with that, Q equals mc delta T, or Q MCAT. And what each of these stands for, Q, of course, is heat. M would be the mass of your substance, T, the temperature in Celsius, and C, the specific heat, either in calories per gram Celsius or joules per gram Celsius. And we say temperature is in Celsius. It doesn't matter in this case because your delta T will never be negative, right? In that delta T is the change in, right? Because if we remember delta, that means change in. And so we're looking at the change in the temperature, right? Not the specific temperature. Okay, so a calculation using QMCAT. So here are some values for things that we will need, right? Things that were shown on the last slide. If we back this up, right? Heat of fusion, heat of vaporization, delta H of fusion or freezing, delta H of vaporization or condensation, right? Those are things that are on there. And then specific heats, right? like we said in the QMCAT, C, specific heat, and ice, water, and vapor, the solid, liquid, and gas phase of any substance, has a different value. For this, they are given here. And then we do some calculations, like if I were to say, calculate the heat required or enthalpy change involved in converting 3 moles of water from 10 Celsius to 111 Celsius, we could do that, right? So we're going to break this up into 5 sections, right? We are going to be heating the ice, because hopefully you know that under 0 degrees Celsius, water is a solid. We're going to then be melting the ice, then heating the water, then boiling the water, and hopefully you know that over 100 degrees Celsius, water becomes a vapor, and so we're then going to be heating the steam. So using our molecular mass of water, right, we have our 3 moles. We are converting the moles to grams in this step here. We are then using QMCAT, right? The M here, the C here, and the delta T here. And then multiplying by the kilojoules to joules conversion, right? Because we're going to have this in kilojoules because, right, our heat of fusion here is in kilojoules, so we're just going to put everything in kilojoules. We could have just as easily left everything in joules, but kilojoules makes it a little easier. All right, so our first step, mole to gram conversion. You might not have to do this if your mass is in grams already. We have 3 moles times 18 grams per mole. We then have our heat of, or our specific heat for ice, right, 2.03 grams per Celsius, or joules per gram Celsius. We then have our delta T, right, which would be -10 through 0, which is 10 degrees, right, because we're heating it from -10 to 0, which is the melting point. We then convert from joules to kilojoules, and this is the amount of energy it takes to raise that amount of ice to 0 degrees Celsius, where we melt it. We then melt it, right? Which for this, we don't even have to convert to grams because our heat of fusion is in kilojoules per mole. Great, that's really easy. We just multiply moles by kilojoules per mole, and we get a number of kilojoules. Fantastic. Very easy. So then, right, we're going to figure out how much energy it takes to heat the water. Again, we need our mass, we need our C, and we need our delta T, all right here. Right, our mass, the same thing. C comes from specific heat of water, and delta T, 0 to 100 degrees Celsius, and then convert it to kilojoules. We're then going to boil the water. So again, using the heat of vaporization, 3 moles times our kilojoules per mole, and then heating the resulting steam to the final temperature, right? Again, we have our mass, our C, which came from right here, our delta T, which would be 100 to 111, and then conversion to kilojoules, right? That gives us our kilojoules for that process, and then we just add them all up. So in total, it's going to take 164.8 kilojoules of energy to convert 3 moles of ice to 3 moles of gaseous water or steam. All right, now here's a phase diagram. This relates pressure and temperature. Draw and temperature, right? And we can look at this and determine what state something is going to be in at that combination of pressure and temperature. So there is something listed on here, at 1 atmosphere, so 1 atmosphere, standard atmospheric pressure, that is where the normal melting and normal boiling point are. So in this case, normal just means at 1 atmosphere. But things can exist at any set of pressures and temperatures, and they will have a certain state. Now, one of the things to point out here, triple point, that is where all of our states are in equilibrium. And then also the critical point, which is anything past that pressure and temperature, right? So in this area out here, things will become what's called a supercritical fluid. And we'll talk about those in just a second. So one thing about phase diagrams to notice is that you can tell which phase something is densest in depending on this line right here and whether its slope is positive or negative. So if the slope is positive, think about as you're putting more pressure on something. In this case, right, looking at this diagram, it will become a solid as you put more pressure on something at a variety of temperatures, right? Now, that means it is densest in the solid phase. If, however, instead of this, we had something that looked like that, right, as you put pressure on it, right, it's more likely to become a liquid, which would mean that substance would be denser in the liquid phase. So that is a way that looking at a phase diagram, you can tell what phase something is densest in. Okay, definitions. You can read these. You can pause the video at this point. You can write them down. But boiling point, atmospheric pressure and vapor pressure are equal. Normal melting and boiling, that is melting and boiling specifically at 1 atmosphere. Note, some substances do not have a normal melting or boiling point. Triple point, combination of temperature and pressure, which all 3 phases exist in equilibrium. And the critical point, a combination of temperature and pressure beyond which a substance becomes a supercritical fluid. And supercritical fluids, so they're pretty cool. You can look up more information about them, but essentially they have properties of both gases and liquids. They have variable shape and volume like a liquid, but can pass through substances like a gas. And they dissolve many substances like a liquid. One supercritical fluid that you will see used quite a bit is supercritical CO2, and it is used to extract things like caffeine in a decaffeination process. So decaffeinated tea and coffee a lot of times is put through a process where the caffeine is extracted by supercritical CO2. And so that's about it for the basics of states. We will look at solids, liquids, and gases all on their own in a little more detail in some other videos. But there you go. That is the basics of states, phase diagrams, and phase change calculations. All right, I will see you in class.